Hello everyone, and welcome to today's presentation, Deploying Kubernetes in the Enterprise. My name is Pat Devine with O'Reilly Media, and I'll be your facilitator for today's presentation. Today's webcast is being brought to you by IBM. IBM is a leading cloud platform and cognitive solutions company, restlessly reinventing since 1911. IBM is the largest technology consulting employer in the world. IBM Cloud is the cloud for smarter business that empowers you to build industry-based solutions to solve real-world problems built for all your applications, AI-ready with Watson powered by data and secure to the core. Get hands-on with IBM Developer technology at developer.ibm.com. Your speakers for today's presentation are Dr. Brad Topol. Brad is the IBM Distinguished Engineer leading efforts focused on open technologies and developer advocacy. Brad is a Kubernetes contributor, serves as a member of the Kubernetes Conformance Workgroup, and is a Kubernetes documentation maintainer. He is a former member of the OpenStack Foundation Board of Directors and OpenStack Core contributor, and was the project lead for the OpenStack Interoperability Challenge effort. He is a co-author of Identity, Authentication, and Access Management in OpenStack, a book published by O'Reilly Media in 2015. We also have Michael Elder. Michael is the IBM Distinguished Engineer for the IBM Cloud Private Platform. Michael holds a BS in Computer Science from Furman University and an MS in Computer Science from the University of North Carolina at Chapel Hill. He has numerous awarded patents and has been honored with 2 IBM Outstanding Technical Achievement Awards. His passions include solving customer problems to enable them to provide better experiences for their user. Also joining us for today is Jake Kitchener. Jake is a senior technical staff member and lead architect for the IBM Cloud Kubernetes service. He is focused on scale, performance, availability, and delivery at public cloud scale and speed. Jake holds a BS in mathematics and computer science from the University of North Carolina at Chapel Hill. His passions are cloud architecture and delivering delightful user experience. We are very excited to have Brad, Michael, and Jake with us to lead this presentation. We will get started with the webcast in just a moment, but first I wanted to go over a little housekeeping to help get the most out of today's presentation. We have the group chat feature for you all to communicate and interact with, which is located in the training platform at the bottom of your screen. In your widget tray, the icon that says group chat. Please note that the group chat is part of the webcast recording, so do not put any personal information in, like your email address. We also have the Q&A widget at the bottom of your screen. Feel free to post your questions and comments at any time during today's webcast, and our speakers will be addressing them there as well. I do want to let everybody know that we are recording today's webcast, and we'll have it ready within 24 to 48 hours, which you'll receive an email as soon as it's ready. All right, it looks like we're all set to begin today's presentation. At this time, I'm going to pass it over to your first speaker. Brad, you're all set. You can take it away.
Okay, thanks, Pat. So thanks to everyone for joining. Today, we're going to talk to you about deploying Kubernetes in the enterprise. We'll start by, providing some overview of Kubernetes, some background information, some of the basics, some of the history, and then you'll see we'll progress into some more advanced topics tailored and suited for the enterprise. So we're going to get rolling. Thanks for moving that forward. So what is Kubernetes? Essentially, it is enterprise-level container orchestration. It is a platform, a layer that allows you to provision, manage, and scale applications that are based on containers across a cluster. You manage infrastructure. It manages resources that are needed by applications, including volumes, networks, secrets, and many, many other resources. Kubernetes has what we call a declarative model. In many ways, you get to just declare what you would want Kubernetes to do, and it goes off and handles all the details. It's a very elegant model that simplifies both what happens and how things execute, as well as being able to understand what the desired state should be. And if you're curious, the name Kubernetes is ancient Greek for helmsman, so you'll hear a lot of helmsman-like terms related to the Kubernetes projects that you'll see. So if we go to the next chart. So just a little bit of history. Around March 2013 at PyCon, the notion of using containers was introduced, and the notion of, and Docker was introduced as well. Basically, Solomon Hykes gave a presentation and said, hey, you know how we're used to normally deploying web apps where we're using virtual machines, and you know how they're really kind of big and they take a while to start up and they take a while to snapshot and they use a whole bunch of resources. Well, I've been looking at these Linux processes and Linux operating system, and it turns out we're starting to get to the point where we can take a process and provide its own little file system, provide its own security and isolation, and we can kind of make that sort of our replacement for a virtual machine. It's a lot lighter. It starts up in much, much more quickly than a virtual machine. And let me show you some demos of how this works. And so they gave a great presentation. People saw the potential for having a much smaller unit of something to deploy as a web application. It's a much smaller unit than virtual machines to manage, greater efficiency, a lot of benefits. He said he'd make this open source, called it Docker. And so that was really the first notion of containers, and people got very excited about it. As more and more people learned about containers and Docker and using it, turns out Google had been using containers themselves for many, many a year, and they had a lot of experience running container-type applications and how to orchestrate those applications. And so when you're using, you know, services at Google, whatever, search or your Gmail, believe it or not, everything's running in containers over there. So they were kind of saying, you know, we got about 10 years experience doing this as well. Why don't we let people in on what we've been using as software to manage and orchestrate our container management? And that was Kubernetes. So we now had a new open source project, and that got people a little bit excited. So they were very much interested in it. But people get more excited about open source projects when it's not a single vendor open source project, when there's a foundation that supports the project, there's a level playing field, there's open governance. Those are typically what's necessary for an open source project to really get growth, explosive growth and traction across the world, across communities. And so fortunately, what happened in 2015 is the Linux Foundation created the Cloud Native Computing Foundation. And this was focused on container-based cloud applications. Google was kind enough to donate Kubernetes as its seed technology for the Cloud Native Computing Foundation. The Cloud Native Computing Foundation has taken that seed technology project, added several other projects around Kubernetes that support it, like monitoring and logging and a whole bunch of other stuff that's really valuable. And through the CNCF, it's grown to having 250 member companies hosting 17 open source projects, and they've done a lot of work with conformance certification. So they make sure that there's over 60 vendors that distribute Kubernetes. They make sure that all those distributions are interoperable. So you as a customer or as a user, you know, you should have workload portability. God forbid one environment that's providing you your Kubernetes support, you don't like it for some reason, you should be able to quickly and easily move to one of the other 59 different platforms. So a lot of things have gone into the growth of Kubernetes. Next chart, please. Just real quick on the Kubernetes architecture. On the left, there's user interfaces. There's a command line interface called, I like to call it kubectl. I'm sure I'll be people that don't like that name, but I call it kubectl, so I'm going to use that. But there's a Kubernetes master node, and there's a whole bunch of worker nodes that run out on the cluster. And on those different worker nodes are where the containers will get started up. Now, as we'll see, and we'll go look, the containers are placed in an encapsulating unit called pods, and we're going to go into more detail about what that means. But if you look, it's a pretty straightforward architecture with a master node and a whole bunch of worker nodes that are running in the cluster to run your workloads. Next chart, please. So when they were working on Kubernetes, they made a decision. They said the smallest deployable unit that we're going to worry about is not going to actually be a container itself. It's actually going to be something called a pod. Through all the years of experience that the people who created Kubernetes had, they realized that typically you have multiple containers that are grouped together. And so they made the decision that the proper unit of deployment would be a pod. And if you look at what's in a pod, there's a picture here on the right. A pod will have multiple containers, multiple maybe volumes attached to those different containers. And the pod itself will have a single IP address. So if you look at what happens with these applications that are in the same pod, they share an IP address and they share port space. So they'll all run on different ports. They'll share the same host name. They can communicate using native inter-process communication. They can share mounted storage. And then in contrast, if you have applications, your containers in different pods, those are going to have different IP addresses, different host names. The pods that are running, even if they're on the same node, if they're in different pods, they might as well be on different servers. And so the classic design question that you ask when you're designing your pods is, will these containers work correctly if they land on different machines? If the answer is yes, then they can be in different pods. Next chart, please. So a lot of features around pods that are provided by Kubernetes. You can create pods, list pods, delete pods. You can run commands in your pods containers. So there's an exec command to run commands. You can copy files to and from the containers in your pods. There's some really nice port forwarding that allows you to connect to your applications that are running in those containers in the pods. Kubernetes has a lot of support for health checking and making sure things are running. So there's also support for liveness probes to make sure your pods are alive. Readiness probes, make sure that your containers and your pods are ready as well, and persistent volume storage. I mentioned earlier that Kubernetes uses a declarative model, and one of the ways that it does this is with its YAML specifications. And we see a very small one here on the right. And a lot of the YAML specifications in Kubernetes take the same structure. If you look at the top, you typically declare your API version, so you know what you're using, what API you're using for your features. You've got a kind field. In this case, we're declaring a pod. You'll have some metadata. Typically, we'll have like the name of the pod. And then you have a spec, which stands for specification. And here in the specification, we're actually just saying, in this pod, we're going to have a container, and there's going to be an image. Nginx is going to be the actual container image that we're running. We can give a name for that container, and we can actually say the port that's there. And there are commands using the command line kubectl to actually create the pod and actually say, use this specification to go do what I want. And in this case, it's start up an Nginx container image. Next chart, please. So having a single pod is good, a nice little abstraction. But the real power of Kubernetes comes from its built-in replica support and built-in support for things like auto-scaling and restarting failed pods. And one of the ways that Kubernetes does this is with replica sets. So in a replica set, you've got a controller that's going to worry about keeping several copies of your application up and running. So the pods they'll be managed by a replica set, and if they fail and you don't have the number of replicas that you want, Kubernetes is going to be smart enough to start more up so that you have the number of replicas that you've declared that you've wanted. And so on the right, we have a little more complicated specification. Again, we'll start at the top. We've got an API version. We get to declare the kind of what we're specifying, the kind of resource. And in this case, it's a replica set. Then you'll see some metadata, the name of the replica set. You'll see some labels. The magic of Kubernetes is a lot of a lot of its controllers, like replica sets and the other ones that we have, they identify what pods they're going to manage by using labels and key value pairs of those labels and selecting on them. So it's very dynamic. You know, what pods are managed by the replica? They're doing key value pair matching on the labels, and so you'll see in the specification that in this case, it wants to have three pod replicas. It'll declare what labels it's matching. And then underneath at the lower part of the specification, you'll see where it says the template. That's the template for the pods that are going to be the replicas. And as you might expect, the labels that are on those pods are the same labels that are the ones that are used by the replica set to then match those pods. So you see kind of a repeating of some values there, and that's why that works. And then you see that nested specification at the bottom. So a replica set doesn't only specify itself, it's also specifying you know, what are the containers in the pods that are managed by the replica set. And in this case, you know, we've got a different type of application running, a web application. And again, so we can start this up and use kubectl create or kubectl apply to start it. But what is nice is we're declaring there to be three replicas. Kubernetes will then worry about making sure there's always three replicas. If one of them fails for some reason, it will start another one up. Having that built-in failure resilience is huge, and there's been a lot of articles where big major commerce sites, some type of failure happened in some portion of it, but they didn't have to really do anything because Kubernetes saved the day by recognizing some of the pods had failed and restarting them in different areas. So a lot of power here. Next chart, please. So more examples here. You can start with, say, three replicas in your specification, but then you can take that same specification and change that value to 6 and use a kubectl apply command. And now Kubernetes will see that you've changed your mind. You've declared not that there's 3 replicas, but that there should be 6 replicas. And again, that model of you declaring what you want the state to be, Kubernetes takes responsibility for making sure that you go from 3 replicas to 6 replicas. And so that's the only change that you see in that specification on the right-hand side. Also, you'll look on the left. I'm not going to go through it, but you can easily delete replica sets. There's commands for describing how you want the auto-scaling to occur. We might see more of that later. So a lot of functionality here where you declare what you want and you let the system go deliver what you need delivered. Next chart, please. So we have a world in Kubernetes where we have all these pods running, and they can sometimes be destroyed and restarted on different machines. And so if you want to provide the function of load balancing across all, say, your web applications, if they're all running in different pods, you'd want a load balancer. Now, the nature of Kubernetes, where it's handling, worrying about the different pods and that they have an IP address and then they can be terminated and be running on a different machine, there's a lot of dynamicism there where Kubernetes realized most load balancers aren't going to provide us what we really, really need. So built into Kubernetes is a Kubernetes service object, which is an interesting term, but it's essentially a load balancer for a group of replica pods. And so what happens in this case is when you create a Kubernetes service, it's assigned a virtual IP. It's also called a cluster IP. And that's the IP address that people should access your web application through that IP address. And it's going to load balance across all the pods that were in, say, the replica set that's been associated with this new service object. That cluster IP address is stable. It's appropriate, for being used in DNS services. So that's the way to go. And readiness checks are built in. So if by chance some of your pods go down, that service object is keeping track of some of that stuff, and it's going to make sure that it's only going to send your traffic to your pods that are actually running. On the right, you can see some basic kubectl commands for how we can actually start a service and how that works. And you worry about the port that it runs on, what port the containers run on, and all of that is described on the right there. Next chart, please. So, seen a lot of power already in Kubernetes. We've talked about the built-in support for replica sets. So Kubernetes is helping you out, showing you where, how many copies of your pods are running and managing that. But what about when you want to release a new version? You want to upgrade to a new version of your application? That's not built into replica sets. And that stuff can get really tricky when you want to roll out a new version. Fortunately, there's another construct in Kubernetes called deployments. And deployments can actually manage not only the replicas, but releasing new versions of the replicas. So with a Kubernetes deployment resource, it's going to enable you to easily move from one version of your code to the next version. It'll help you to roll out that new version without downtime. It'll use health checks to make sure the new version is running correctly. It all runs server side, so you could even kick off a deployment from a plane with an intermittent connection and all would be well. And so if you look on the right, we have that same pattern of the specification similar to a replica set. The difference at the top, there's a different kind. It's not a replica set, it's a deployment. We add some key value pairs. We can add labels, and also we can add annotations. The difference is labels are used for selecting pods and which pods you want access to or to control. And annotations are more like providing information for tools or providing information, in this case, say what version of our application is running. But then after that, it gets pretty similar to replica sets. You can declare how many replicas there are, what labels you are using to match. And then there's one other feature here that's a little bit different. It's what kind of update strategy do you want to use? The most popular is a rolling update. So you get to control through a declarative fashion how you want your update to occur. Do you want to have, let's say you had 5 versions of an existing version of your application. Do you want 5 of the new versions started up, so you've got a total of 10 out there before it decides to terminate all the old version? That's called a blue-green deployment. Or do you want a mix of the two because you want a little slower rolling out of the new version? So there's some values here. How many unavailable nodes can there be? So that'll control how many extra nodes, how many nodes are allowed to go down. And then if you want to have extra nodes to make sure that there's no problems, that's the max surge value. So you've got a couple values to play with there to control how you want your rolling update done. And, and you can go look in different places and you can see how you can set those different values to get different types of deployments that meet your needs. And then the rest of this is the same thing. Here's the image that we want to be in our pods that are managed as part of these replicas. So a lot of power there. If we go to the next chart, please. So again, there you go. Again, what we can see here is scaling the deployment is the same as replica sets. You change the number in the replicas, that's there in red on the right, and you can reapply, and by doing that, the deployment can increase your number of replicas. Next chart, please. And now if you want to update an image, you can look at what we change in red. We add an annotation to say we're going to update the version of Nginx. We can control our rolling update features, max unavailable of 1, and you can add an extra one, an extra node to as you're doing the rolling out of the new version if that's what you need to make things go well. And then you can see in red at the bottom, we're changing the image version. So we're going to a newer version of Nginx. And so all we do is we change those values and we use the kubectl apply command at the bottom right. And when this runs, it's going to see that the new specifications coming into Kubernetes, and using the declarative model, it's going to decide to update that and meet the new specification. So in this case, with the new version. Now, I'm not going to go into it very much, but there are wonderful commands that allow you to control the speed of that deployment. You can check the status of it, you can pause it, you can resume it, you can roll it back, and check the history as well. So a lot of built-in features into deployments that make rolling out a new version of your application wonderful. Next chart, please. So at this point, I'm going to hand over to Michael Elder, and he's going to take us through some more advanced features of Kubernetes. Go ahead, Michael.
Sure, thanks, Brad. So the key thing here is what we've gone through so far. How can we represent the different parts of your application in an easy to manage way through a declarative text-based format? We'll talk about why that's important in continuous delivery in the next slide. But the next part of how I deploy and manage these things comes into how do I scope and how do I provide proper access control for each of the different applications. You can think of it sort of as the nested layers of encapsulation. I built a container image, which manages my process, helps me abstract how the process interacts with the rest of the operating system, how it interacts with my data on the file system. We wrap that into the pod, and the pod said, here's how a container or a collection of containers and a collection of volumes works together as a single unit of deployment. And then we wrapped various layers of replica sets and deployments that Brad's gone through to understand how do we manage and deploy those objects. Now, once we get into many different applications, we want to understand how do I scope application 1 from an application 2 to ensure that that collection of deployments, of stateful sets, of daemon sets, these are other concepts that you can get into in Kubernetes as well. How do they isolate perhaps their network traffic, or isolate who is allowed to update them, or isolate things like quota? So namespaces are that next level of concept that sort of takes the orchestration strategies you get with something like a deployment and begins to provide that layer of access control. And Brad talked about the service object. This is simply kind of an example of where this comes into play. You've got perhaps one namespace, which is managing application pods. They consume data. Then I might have another namespace, which is managing some kind of stateful data pod. So in this case, there's another concept called stateful set, which we haven't introduced in detail, but you can extrapolate. It's typically used for workloads which are stateful. And so if you think about Mongo or Redis or a traditional SQL database, I might decide that because of the team that manages those pods, or because of the special access control and understanding who has the ability to view, edit, modify, et cetera, that data, I want to encapsulate those in their own namespace, and then expose those services through this Kubernetes service object and make them available to applications which are going to interact with that data. So the neat thing here is that namespaces provide us with that level of access control and governance as well. Now, on the next slide, what do all of these concepts come together to help us do? So ultimately, there's a number of different factors here. You've got things like Kubernetes, which provides us with a orchestration pattern around containers. And we have these principles of continuous delivery, which have been driving us to be able to make updates in a more incremental fashion. And then we have architectural principles like 12-factor, right, which help us describe, here's a set of best practices for how to build applications. So Kubernetes is a technology to enable us to understand how to deliver containerized applications in an easy, predictable way. A philosophy around continuous delivery that says, here's how I need to make changes in my environment and how to apply those changes in a very continuous, incremental way. And then a set of architectural principles like a 12-factor example. So all of this comes together then to enable us to really take advantage of each of these different categories. I can use small incremental updates to my container image and push updates, as Brad showed in his example. I can make updates to the YAML configuration. So we didn't really get into details about managing things like config maps and secrets. But in 12-factor, there's this principle of how do I externalize environment config. Kubernetes offers us a very direct way, sort of a one-to-one of 12-factor principles say follow it and do something like this, and Kubernetes says here's how exactly I manage that with a resource kind called a config map or a resource kind called a secret. And so now I can update container images very incrementally. I can update the configuration YAML very incrementally. And so now I can begin to apply continuous delivery to the way that I ship applications very easily. I can drive more small batch changes. All of these objects from the source code and the Docker files, which help us build a container image, to the Kubernetes YAML resources are all things which are very easy to source control. And in fact, depending on how much you adopt technologies like Git, you can actually do things like GitOps and can use that as a simple way for many styles of workloads or applications to deploy a approved set of configuration changes in different environments. Again, because we've containerized all the things, so think about how you're going to bring data workloads and other stateless workloads into this environment. It becomes an easier way to fulfill developer requests for new environments. Instead of having developers stand up one-off processes for each of the different pieces they need for their app on their laptop, we can help them recreate an entire application through a set of Kubernetes YAML documents and container images. And if it's easier to create those production-like environments locally, I can begin to shift some of the operational practices. For instance, how do I collect and view logs for those containers? How do I collect and view health metrics for those containers? And then if I have other practices around things like auditing, backup recovery, serviceability, or debugging, by moving this capability and adopting sort of these three categories of things, Kubernetes is an enabler technology, continuous delivery is a philosophy, certain architectural principles that help me build applications that fit neatly into these two columns, then I can actually begin to absorb some of the way that my production team operates my application. And I can do that so that developers get more insight into understanding how did their applications actually run in production, which means they can begin to optimize to make sure they get the right kinds of logs when an outage occurs or an incident occurs, or produce better health metrics that help us understand and predict when an application's behavior is about to degrade. So that becomes a very powerful way to bring those operational practices earlier into the development lifecycle. And of course, everything we've talked about here is either easy to source control or easy to program through a command line. And that means it makes continuous integration and therefore the automation not only of how I build, but how I deploy and promote things more straightforward as well. And that ties into how do I drive a highly automated test validation cycle that helps me drive that feedback into my development process earlier. So the key aspect here is that these technologies and these principles have evolved hand in hand. And so they understand that a lot of the principles of continuous delivery, like small batch changes, source controlling all of your objects, managing more production-like environments earlier in the development lifecycle, managing more operational practices earlier in the development lifecycle, all of those things fit neatly together. So for an enterprise, where does this become really powerful? So on the next slide, what I'm going to challenge you to think about is how can you apply these technologies as you adopt both continuously improving how your data center operates today, how you begin to adopt public cloud technologies where some of these things might be managed as a service consumption model, and everything in between. So if you think about a hybrid cloud architecture, you're leveraging existing enterprise API, maybe things that are more data-centric or transactional for many traditional enterprises today. And then perhaps you're leveraging newer styles of cloud service like AI or blockchain or Internet of Things type technologies that help you enhance your overall user experience. And then you've got some sort of bridge of how do I get my existing assets to take advantage of newer capabilities to create something that really engages my users or helps me disrupt my existing marketplace. Because all of these different aspects are very standardized in terms of how container images are packaged and deployed, because of how all of these principles of Kubernetes abstracting things like the networking model, we see that object, or with pods having their own local IP, or things like storage, which we didn't get into in detail, but there is an abstraction model for how Kubernetes mounts storage into those volumes that we see in the pods. And so because there's that common abstraction layer, it means I can run a Kubernetes orchestrator both in my data center on traditional bare metal VMware OpenStack type infrastructure. I can manage it where I'm consuming traditional compute from a cloud provider. And I can also manage it as a completely managed service where I simply go to a cloud provider, ask it to create a Kubernetes cluster, and begin leveraging that as part of my application. And now I have a way to build a portable programming model that can work across any of these types of zones or a blend to help me address concerns about common application architecture and development, common portability, common ways to integrate across that spectrum of different kinds of API, provides me with a mechanism where I can still keep data close to my data center where it's under certain compliance or other governance controls. Because everything's easy to automate, I can manage how do I deploy, and then also how do I standardize the collection of operational data as part of my ongoing service management. And then I can set up certain and literally drive through the definition of documents and YAML files, the network policies, the quotas, the pod security policies, and other forms of security and compliance across the spectrum. So next slide. And so one of the enabling technologies that can help you drive this, right, with Kubernetes as a way to manage data that's both, or pods, excuse me, that are maybe more typically enterprise API, transactional API, or data-centric API managed in your data center, and more traditional 12-factor, or more commonly thought of as 12-factor or cloud-scale microservices in a public context. This now becomes this sort of hybrid model in between. And if we go to the next slide, one of the ways to think about how you manage packaging and distributing across these zones is something called Helm. Helm has evolved as a sort of de facto community standard for the packaging of Kubernetes applications in the community. Helm allows you to take all of the YAML files that we saw earlier, drive a collection of parameterized values so that perhaps the specific resource limit and quota, or excuse me, the resource request, which is sort of the lower limit of how much memory a container should be given, and the limit, which is sort of the upper boundary of how much memory you allow it to have, or CPU that you allow it to have. I might decide those are things I want to parameterize. Or I might decide I want to parameterize the type of storage that the application consumes, because my storage classes that are in a public provided Kubernetes service are different than my Kubernetes services that I deploy and manage in my data center. So Helm helps us drive that kind of abstraction model and drive a basic notion of how do I drive the first installation and the upgrade and the rollback. Next slide. And so some basic concepts, which we're not going to get into in a lot of detail, but I want you to at least understand some of the terms. We can create what's known as a Helm chart. The Helm chart, again, everything here is somewhat nautical language because of the Kubernetes theme here, right? Kubernetes is a nautical term. So the chart provides sort of a map. It's all of the Kubernetes resources that I need for an application. We collect these into a repository, and there's a number of community repositories that are available that you can consume many different kinds of applications that are already built for Kubernetes. And when it's deployed, we call that deployed object a release. So the release is actually the instance or all of the instances that are created. So a Helm chart might create the deployment, which is a combination of the replica set and pod that we saw earlier, config map or secret, which are used by the application, the service object, which is used to expose the networking, and maybe even other policies as well. So it helps us actually take the bundle of things and make them more portable across each of those different zones. And so now I'd like to turn it over to Jake, who's going to take us through more of the concerns of how an operator interacts with their cluster as they're managing it. Jake?
Thanks, Michael. So yeah, as Michael mentioned, I'll talk a little bit some of the operational characteristics of a Kubernetes cluster. And we'll start talking a little bit about networking. So we talked a little bit earlier about the concept of Kubernetes services, and I'm going to kind of expand upon that a little bit. So, you know, we've gone over this idea of, hey, it's really easy to define and deploy my applications, and then also to be able to package and roll those things out to into production. But how do I make those things accessible from outside of my Kubernetes cluster? And this is where we get into the realm of load balancers or also ingress. So the idea here is that again, through very simple YAML definitions, you can define how you want to expose the applications and services that you've created in Kubernetes to the outside world. And in this case, right, we can simply expose our hello service to the outside world via an ingress on a host name of our choosing, right? So if I had helloapp.com already registered and I had my DNS pointed at my Kubernetes cluster, then I can simply create these ingress objects, and then Kubernetes is going to do all the work internally to make sure that any traffic that's being directed towards my Kubernetes cluster for helloapp.com on the root path is going to just get directed to the hello service. Now, obviously, this is an extremely simplified example here, but you can certainly see where, if I had many applications to support helloapp.com, I can create additional paths for various components within the service to expose different portions of the application. Load balancers are similar to ingress in that they're a way to expose my apps and services to the outside world. But in this case, it's just a traditional layer 4 load balancing concept where, if I create a hello service and I expose it as a load balancer, then I'm just going to get a single IP address that is then, externally accessible to access that service. And I'll do a quick demo of that here in a few minutes. And then, pod networking, I'm not going to go into great detail here, but essentially, Kubernetes has this concept of pod networking that allows all of the pods within a Kubernetes cluster to communicate with one another through, a basic overlay network to make that very straightforward and easy for the interpod communication. The other thing I don't reference here is kubedns, which is, I think, a very important part of Kubernetes. It's sort of half of the service discovery concepts of Kubernetes. So kubeproxy is going to do all the network routing and load balancing within the cluster, and then kubedns is a component that basically provides DNS services to everything in the cluster, so that service A can reach service B by simply sending requests to service B, like http://service B, and then Kubernetes is going to ensure that that traffic gets routed to a pod that is implementing the service B service. Another interesting part of Kubernetes networking is the concept of network security policies. So this is a really great way to basically build essentially basic, network access control or firewall support within a Kubernetes cluster. It's a very flexible concept, and it's been kind of growing over time as Kubernetes has matured. So initially, it was really just intended to be able to define how, pods can talk to one another. So, pod A is allowed to talk to pod B, and pod B can talk to pod C, but pod A can't talk to pod C. So it allows you to basically set up, access control for networking within a cluster just through YAML definitions. And then, some of the things that have been sort of introduced over time is the ability to do things like we have in this example, which is control ingress and egress through IP blocks. So this is, a great tool for basically controlling outbound access from the cluster for security purposes. So, frequently network admins and security advisors will say, look, inside the cluster, maybe you have pretty free reign as far as network communication, but, we're really trying to restrict, what is accessible outside the cluster, whether it be on the intranet or the internet. And so rules like this can make it really easy to define through code, what services you can access outbound to get out of the cluster. So Michael also made a brief reference to storage in Kubernetes. So, I'll talk briefly about a couple of different types of storage. So in Kubernetes, I'd like to think of there being two different scopes for storage. So there's storage that is scoped at the node level, and there is storage that is scoped at the cluster level. So we'll talk about node scope storage first. And you'll see there's three types here: empty dir, host path, and local. Essentially, what creating storage of this type allows your pods to access storage that is local to the node that is running on. So, empty dir is great if you just need some scratch space, basically to store things temporarily. It's oftentimes used for one container in a pod to transfer information or data to another pod. Or another container in the same pod. So, sometimes this will be used for like a logging mechanism, right? Where, container A is writing to disk and performing, its primary function of whatever that pod is, say, serving a web page. And then container B may be reading from that disk to then send logging information off to some, external logging service. So this is something that empty dir is really great for. Again, it's not persistent storage. It gets wiped. Pods get moved to other nodes all the time, so you can't assume that, your empty dir is not going to come with your pod if it gets killed and moved somewhere else. Host path is a storage type that's great if you have a pod that needs to make modifications to the underlying host system. This is not, I think, typically recommended. You certainly shouldn't be using this to persist data for, your database or your web server or something like that. But a lot of times there may be the need to either monitor or modify something in the worker node's host file system, and host path is a great option for that. Local is, it's not new, but it's less often used storage type, and it is kind of maturing rapidly. This essentially allows pods to access raw disks on the host file system, or on the host system. This can be interesting if you have some unique requirements as far as accessing potentially, like a network attached or a clustered file system is one place where that may be used. Or it's also great if you are building a shared file system service on Kubernetes. It may need access to local disks. I think a more interest and more commonly used would be cluster scope storage. And basically, there's three key things to consider when we're talking about shared storage that's cluster scoped. And cluster scoped essentially means that no matter where in the cluster your pod lives, it will always have access to the storage. So the basis there is persistent volume. This is just an object that basically provides Kubernetes a method of understanding of how to access that storage on the network. A claim is basically just a binding between essentially a consumer of the persistent volume and the persistent volume itself. So, pod A could say, I would like to place a persistent volume claim on, persistent volume foo or whatever it may be. So it's really a bookkeeping mechanism as much as anything. And then I think the most important aspect here is volume plugins, which are essentially used to support all kinds of third-party storage types. So, your cloud provider of choice may have, various persistent storage capabilities available, and volume plugins are a method for vendors to plug into that capability. So I'll talk briefly about user security. There's tons and tons of information available out there about user security, but I think the most important thing to note is that, for authentication, the most common things that you're going to interact with are OIDC or OpenID Connect tokens or service account tokens. So OIDC tokens are typically used for connecting to, a cloud provider, or you may have a shim that allows you to authenticate with some backend LDAP service. Service account tokens are Kubernetes' own internal mechanism for doing authentication, and they're used for allowing pods to authenticate back to the Kubernetes system itself. On the authorization front, typically we're referring to what Kubernetes calls RBAC, or as it sounds, right, role-based access control. And there's 4 kind of key components to this, and they sort of come in pairs. So you have roles and role bindings, and then cluster roles and cluster role bindings. Roles and role bindings are typically used to provide access to objects within a namespace, and cluster roles and cluster role bindings are typically used to provide access to a broader set of resources, whether that be nodes, namespaces, or in certain situations where you want to have a broad definition of the cluster role, which is the what to do, and then the binding of who can do it can be scoped down from there. Michael already spoke a little bit about using namespaces to help scope access control. And then in hybrid environments, it's important to consider when you've got multiple Kubernetes clusters, what are your best options for basically providing like a seamless method for authentication across multiple Kubernetes clusters? And I'm not going to go into detail here, but I would recommend doing similar investigation into concepts like federated identity or impersonation, are both methods to deal with authentication in hybrid environments. And then on the right-hand side, you can see there's just a brief example of what a cluster role might look like. So, here I've got a cluster role named viewer, and really the idea here is just that, we're defining the resources here, our deployments or replica sets, and then the actions that you can take on those things, get, list, or watch. So it's more of a viewer concept. And then a binding, which is basically providing that role to a particular user. So here, I'm binding the viewer cluster role to a subject, in this case, a user, CICD at IBM.com. So it's that binding that actually provides, CICD with that viewer role in the system. All right. So I think earlier we mentioned a little bit about auto-scaling, and I was just going to do a quick demonstration here. There are a bunch of different types of autoscalers out there. I think, the most commonly used is the horizontal pod autoscaler, and it's called horizontal because it scales out, not up. Up would be the vertical pod autoscaler, which just makes pods bigger. Horizontal pod autoscaler just makes more of them. So quick demo here. Let's see. All right, so to get started, we need something to actually auto-scale. So I'm going to create a quick little Hello app application here on my system. And I'm going to expose that application as a service. And I'm going to just get this kicked off real quick, and then I'll talk a little bit more detail about what each piece is doing. And then I'm going to give Kubernetes the information it needs to begin auto-scaling that particular thing. So this is basically saying, hey, if the CPU utilization of the Hello app ever gets to 80%, then I want you to create more instances of it. And now I'm going to drive some load against that thing. So what I will do is start watching these pods, so we can see I have my app running, and now I have my load being run against that. And we can see that I have my autoscaler. So, I'm sort of compressing time as much as I possibly can to make this thing a short demo. But the idea here is that, I've got my Hello app horizontal pod autoscaler created. It has a definition of what's the minimum number of pods that I want to have running, or the maximum number, how many are currently running. And then under targets, you can see my target is 80% CPU. It doesn't know how much CPU is being used yet. It takes the system some time to start gathering data about that particular application. So it's got basically just sort of like some time before it can start collecting data. All right. And then if we want to, so earlier we talked about defining deployments, pods, replica sets using YAML. I've used kubectl basically some of the built-in functions to more simply create new applications. But if I want to, I can do git deploy app. And I can see more of the details. This is basically just the YAML that was generated for me by the Kubernetes system. And you can see some of the concepts that we talked about earlier. The template and the spec for this. Here's the definition of container, what image it's using. And then, an important part for the auto scaling is the CPU and memory requests for this particular component. And fortunately, we can see now this has automatically scaled up my application to run 5 pods to provide more capacity and scale for this particular small application. Get HPA. So we can see now we're running 4 replicas. We're obviously still at a very high CPU utilization, so we'll continue to add more and more replicas for me over time. And that's basically it. If I remove the load from the system, then the autoscaler will, over time, slowly reduce the number of replicas that are needed for that particular application. So that is it for the demo. So that's it. Let's wrap up a little bit here. So, I think some important key takeaways is that Kubernetes is really gaining very rapid adoption across the industry for being sort of the standard for application and container orchestration. The amount of growth that it's seen in the last 2 years, I think, is pretty hard to even sort of describe how quickly things have grown. There's some key things that we've talked about today that have sort of helped contribute to that, right? The very simple and straightforward declarative model for building, deploying applications. Some of the nice features like the auto scaling that we just saw a quick example of, having all of those capabilities baked into the actual infrastructure and the system really does take a lot of the complexities of building and deploying highly available and scalable applications, out of the system. I will also leave a couple of links here. So we've referred to a couple of different services from IBM. So one is the IBM Cloud Kubernetes service. This is our, public cloud-based Kubernetes as a service solution. So, very simple one-click interface to go get new Kubernetes clusters up and running. And then also IBM Cloud Private. So IBM Cloud Private is a software solution that allows companies to build and run their own Kubernetes clusters in on-premises locations, even behind a firewall. So that will do it from our end. Thank you all for spending the time to learn a little bit more about Kubernetes today. So Pat, I think that's it from our end.
All right, thanks so much. At this time, we're now going to go to the live Q&A portion of today's presentation. I encourage you to enter in your questions in the Q&A widget there. I apologize, everyone, as well. I'm having a couple of technical difficulties on my end, so I can't see the questions right now. So I'm going to leave it open if you guys have anything in the Q&A widget or in the group chat.
I am not seeing anything from my side.
Yeah, I think there was a question about the charts, and we are making this available.
Yep, I have the slide deck available, everyone, as a download in the resources list there. So if you want to go ahead and refresh your console there, you'll be able to see that, and you'll be able to download the PDF directly to your document. If there wasn't any questions for today, was there any last-minute comments or concerns you guys had for the attendees, or anything else you wanted to cover, or any questions that you could think of?
No, we just hope everyone enjoyed the presentation, and we thank them for attending.
All right, thanks so much, everyone. I wanted to thank today's speakers for an excellent presentation. I wanted to thank IBM for making this event possible. As always, thanks so much, everyone. Have a great rest of your day, and thanks again. Okay, you guys still on the line?
Yeah.
Yes.
Okay, I see your question. I see your thing now about one more question in the Q&A. Was there anything you wanted to address before I end? For everybody still on the line?
I don't know if we could even answer that real quick.
So,
okay, thanks so much. I'm going to end.
Somebody
I
said
see
it was
the one
supposed to
about
start to-
debugging.
Yeah.
Okay, go ahead.
So I think debugging Kubernetes applications on a local laptop, there is Minikube, which is available that you can pull in from the community. That's probably your best bet. Minikube, though, is pretty resource limited. So I think from that perspective, it's a start, but it probably is not going to be enabling all the things that you want or requires additional configuration if you want to set up the same kind of policies and structure that you'd have inside of a typical cluster.
Okay, excellent.
And
Was there
there was a
anything else
question
you
about-
wanted to cover as well while we're still on the line? All right, go ahead.
There's one question about, can you talk about a service mesh? And I'm happy to provide some comments there. I don't know, Jake, if you want to take that one.
Sure. I'll, basically, I think, typically, I think today when folks are talking about service meshes, the most popular, at least in these parts of the woods, is certainly Istio. So you can go to istio.io to learn a little bit more about it. Yeah, I mean, service mesh is basically just taking the service concepts that are available in Kubernetes and taking them one step further. So typically a service mesh will introduce more access control capabilities, more advanced routing so that you can do some live targeted user testing or A/B testing of applications. It has capabilities like advanced metering and tracing, and then I guess just, more advanced service discovery capabilities to allow you to do, global service discovery to expand beyond like a single Kubernetes cluster. There's a lot of other, I guess, things in the service discovery space that I think, you can gain with a solution like Istio.
Okay, wonderful. Any other questions, guys?
That is all that I see right now.
All right, we'll give it a couple more minutes or a couple of minutes to see if anything else rolls in, and then I'll end today's webcast.
So one person did mention that they were having a lot of trouble getting Kubernetes up and running on top of CentOS. I don't know that I have any particular reasons as to why it may be more challenging there versus other platforms. I don't know. I mean, from a cloud-based service, right, we sort of pick our own OS and sort of standardize on that. But I don't know, Michael, from your side, and the more packaged software solutions, have you guys looked at other operating systems and what some of the challenges may be there?
So in our package format with Cloud Private, we support Ubuntu, RHEL, and SUSE out of the box. I think without more details, I couldn't generically answer if CentOS is harder as a platform to automate. I tend not to work with CentOS as much because it requires a lot of interaction with things like the ePal repositories. So that's my personal bias as a developer. But if you're interested in picking up a local version of Kube that's sort of prepackaged, the Cloud Private package that we mentioned is actually on Docker Hub. So you can Google deploy IBM Cloud Private. It'll give you a containerized install of Kubernetes. And as I said, today we test that on Ubuntu, RHEL, and SUSE. But it's a containerized package. So once you have Docker loaded on the host OS, if you don't use one of our package versions of the Docker runtime, from there it's using a fully containerized deployer to stand up all the different pieces of Kubernetes. There's some Ansible that touches the operating system when you deal with things like the kubelet, but that might be a path to try to work around it. But I don't know that I've seen anything generically related to being harder on CentOS versus other OSs. I think pulling it from the community can be challenging just because there's lots of moving parts, which is part of the reason we're trying to make that more consumable. But I don't know that I've seen anything that says it's harder in one OS versus another. And a comment on slides, there's a downloads resources section that you can pull the slides down even now if you'd like to get a copy.
All right, excellent. Any other questions, guys?
That's it right now.
All right, I'll give it another minute, everybody, for everybody still on if you have any questions. Otherwise, I'll end the webcast. Thanks so much. Stand by, everybody, and we'll see everything in the group chat for any questions or in the Q&A tab. All right, about 10 more seconds, anybody, if anybody has anything for Jake, Brad, or Michael. All right, well, it looks like we're all set for today. Thanks to everybody so much for joining us. We'll see you at a future webcast. Thanks, IBM, for making this event possible. Have a great rest of your day, everyone, and thanks again, Brad, Jake, and Michael.
All right. Thank you, everybody.
Thanks all.